Hello, my name is Nadir Talha. I'm an electrical engineering student at Case Western Reserve University, and I'm here to present to you my summer research at MIT on designing multifunctional fibers for testing in vivo molecular fMRI probes. The goal of my project was to design multifunctional fibers that allowed for electrical simulations, optogenetic control and measurements, and also drug delivery and contrast agent delivery. And all of this would be happening in parallel to fMRI scans. This device would eventually be used to develop new molecular fMRI probes and help better understand the brain's structure and function, and hopefully help cure diseases like Parkinson's and other neurological diseases. So some background about molecular fMRI. Here in Alan Jasnoff's lab, MIT, we develop new probes to track calcium, intracellular calcium in the brain. Calcium is a very important marker of neural activity, and the advantage of this probe is that it has the specificity of an optical probe, but also gives us a whole brain view to be able to uncover connections in the brain. This new technique of using contrast agents that would enable us to track calcium intracellularly and is comparable to optical photometry techniques commonly used to investigate local regions in the brain. And so by optimizing this multifunctional fibers I'm making, I hope to give a sort of a comparison between molecular fMRI probes that track calcium and optical probes. So the way I made these multifunctional fibers was by a technique used commonly in the optical fiber industry called thermal drawing process. We first make a preform that is on like a bigger scale, and we use the thermal drawing process to reduce the size of that preform by 100 times or 200 times. This offers like a huge flexibility in like designing the preform and gives us very small features, the sizes at the end. We could also integrate very biocompatible materials and scale these fibers, and we make kilometers of fibers. So it's very easy to manufacture. This is the device I was able to make this summer. It has electrical simulation wires, a microfluidic channel for contrast agent delivery and drug delivery, and also an optical fiber for photometry measurements. We mainly use polymers and composite materials that would be very biocompatible and reduce like neural scarring and neural death, and also matches the mechanical properties of the brain. This is some of the photometry measurements we were able to record from the brain. And so, as you can see, these devices work perfectly, and they're when implanted in the rat's hippocampus. We also were able to scan animals with these multifunctional fibers, and we did not notice any artifacts on our MRI scans. So they were perfectly MRI compatible. This is also some of the expression we got from injecting GCamp, which is a calcium optical probe. And so you can see that the expression was perfectly established. And so the purpose of this research is to be able to probe the brain for long-term experiments and use these like new techniques of molecular fMRI to track calcium in the brain and be able to establish connections between whole brain regions, between like very distant brain regions, and also establish the connections of different parts of the brain. In the future, we'll be able to improve the design of these multifunctional fibers and embed copper and carbon-loaded silicon in the preform for easier manufacturing techniques. It would also measure the impact of artifacts, even if we didn't notice huge artifacts. And we would also measure how much current we want to deliver through our electrical wires. Thank you so much for your attention, and take care.